Hello again. This video is about solving inequalities, and we're still in part 1, but we're doing the second part of part 1. We have talked about already how to solve inequalities using addition and subtraction. We did it with tiles and symbolically. We talked about our addition-subtraction property of inequalities, which says you can add or subtract an equal amount from both sides of an inequality without changing the inequality. It won't change to an equal sign, and it won't change to the other inequality. We did some examples. Today we're going to talk about, obviously, multiplying and dividing to solve inequalities. And so we'll start with tiles again. We have our inequality 3x is greater than 6. So our first step is to build that. 3x is greater than 6, positive. So 1, 2, this is exciting watching me drag tiles. 4, 5, and 6. So I have 3x is greater than 6. And if this were an equal sign, we would actually just go ahead and make our little teams, and we would divide them up like this. And we would have that each x must then be greater than 2. And my question is, does this make sense to you? Does it make sense that if each x is greater than 2, that this inequality is still true? So let's check it. If this number is bigger than 2, and this number is bigger than 2, and this number is bigger than 2, will this whole thing be bigger than 6? Well, say it's 3. 3 plus 3 plus 3 bigger than 6? Sure. 10 plus 10 plus 10, is that bigger than 6? Yes. So it does make sense for us to actually divide our x's out and make them into teams so that we could see that each of one of these is bigger than this part right here. Okay, so, whoops, trying to clean up a bit. Let's do this one. For this problem, we'll have 3 negative x's, and this is greater than 6 positives. You're saying, but Miss Coker, really, this isn't any different. But there is a difference. Let's see. We can kind of have them arranged this way. Okay, so automatically we would want to go ahead and divide these into 3 groups. And we divided them. And in each group we see that we have negative x is greater than 2. And you say, oh, we're done, we're done. Well, maybe not. What's our problem? That's right, our problem is we don't have a positive x. Just like with equations, we don't want to know what negative x is equal to. We want to know what positive x is equal to. So if you remember what we did, if we wanted this to be a positive, we would just flip it over. And then that meant that we had to flip this side of the equation too. But the interesting thing is, that means we also have to flip the symbol. Uh-oh, did I lose you? That, if I flip this one and flip these, then I have to flip my symbol. And so now we get the inequality x is less than negative 2. Okay, hold on, let's check it, just like we checked this other one. If each x is less than negative 2, then our negative x's, okay, so then let's check it. So let's see if this works. If I have negative 3x is greater than 6, and I say this guy here is less than negative 2. Well, what are some numbers less than negative 2 we can check with? Okay, negative 3. All right. So negative 3 times negative 3 is that greater than 6? Well, negative 3 times negative 3 is positive 9, and that is greater than 6. Oh, that's weird. I think we need to try another one. Let's look at another one symbolically. So we'll start with negative 2x is less than, let's say, 5. Okay? If I were to do this symbolically, I would divide it by 2, kind of like when we did with the tiles. And I would end up with negative x is less than 2.5. And then we do our flip thing, where I make this positive, I flip my symbol, and I make this negative. So in our original problem, let's look at our original problem. I'm now going to substitute something greater than negative 2.5 in place of x to see if my inequality holds. So a number that I love to check is 0. 0 is greater than negative 2.5. So I'm going to say negative 2 times 0, is that less than 5? Well, negative 2 times 0 is 0. Is that less than 5? And that's true. Now you see, if I hadn't flipped the symbol, let's do it incorrectly, and we'll have x is less than negative 2.5. So a number less than negative 2.5 might be negative 4. If I put negative 4 in here, negative 2 times negative 4, is that going to be less than 5? Well, no, because two negatives give us a positive when we multiply, and 8 is not less than 5. That is false, so this does not work. Okay, now you may still be a little confused. So this is where you might pause the video, replay it, or we can go a little further forward and you can see if it's starting to make more sense. So our new property here, and this one's very different, our multiplication division property of inequalities. I can multiply or divide both sides of an inequality by the same amount if that amount is positive. But what's going on when we multiply or divide by a negative number is we have to flip the symbol around. So when I take an inequality and I multiply or divide both sides of the equation by a negative number, there's a trick here that I have to flip it around. Now really, what happened before is we had an equation, and when we multiplied or divided by a negative, we would flip. I'm going to try to get these two things together. I'll lock them, group them. Okay, so then we would take that negative and negative and we would flip the whole thing. Well, we flipped our equation too, but when you flip it, guess what happens? It's the same thing. So we never really noticed it before, but we were actually flipping this, and flipping this before, but our equal sign didn't change. Now, this property is going to cause us some trouble, and I can tell you right now, there's going to be some of you on the test that are going to miss this. And so we've made a little song for you. All right, so here's how the song goes, and you need to practice it because we're going to sing it in class. The tune for this song is Pop Goes the Weasel. And you probably maybe have heard this tune another way, but I always think about those little jack-in-the-boxes that you give to babies to scare them to death. The Pop Goes the Weasel song is the song that usually is in those. And the tune goes like this. Dun da dun da 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 dun dun da dun da dun da da dun da dun da dun da 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 dun 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 da da dun. And the way we'll sing the song is multiply by a positive, do nothing to the symbol. Multiply by a negative, flip goes the symbol. The second verse, divide by a positive, do nothing to the symbol. Divide by a negative, flip goes the symbol. All right, now that you've stopped laughing, we're going to move on to doing a couple of practice problems. So here's practice B, and in this problem, we're going to look at 4a is greater than 32, and the way to solve this would be to divide both sides by 4, and we would have a is greater than And so then we would put our 0, we could put 0 here, 1, 2, 3, 4, 5, 6, 7, 8. Here's 8. That's our critical point. We circle our critical point. Numbers greater than 8, let's check. 0, is 0 greater than 8? No. Is 9 greater than 8? Yes. So we'll be shading this direction. Go back and check our critical point. Is it or equals to? No. So it remains an open circle. Number 2, to solve this inequality, we're going to divide both sides by -7. And we'll end up with 1y is less than -3. So here's our 0. 1, 2, here's -3, our critical point. Circle it. Check a point. Let's check 0. Is 0 less than -3? No. Is -4 less than -3? Yes. So we're going to shade this direction where -4 is. Check our critical point. Strictly less than. So -3 is not part of a solution. Open circle. Let's go to a fraction. I know you guys love these. This one, in case you can't read it too well, is y over 5 greater than 4. Now, just like with equations, we can think of this as 1/5 y. Or we could say we have a denominator and we want to get rid of it. So we'll multiply both sides of our equation. Oh, I see. We do make a mistake. Let's finish this one. 5 over 1 will give us 1y. It's greater than 4 times 5, which is 20. So then we might say here's 0, 5, 10, 15. Here's 20. Circle it. Numbers greater than 20, well 30 is greater than 20, so we'll shade this way. It's not a closed circle, it's strictly greater than. So, Ms. Coker, what did you do? Well, I divided by a negative. What did I forget? Flip goes the symbol. So let's check some of our answers in the original inequality. That's why we go back to the original inequality. -7 times -4, which we think is in our solution set, is that less than 21? And that's not true. We have to shade this way. So I'm going to erase the mess I made. I hope you didn't get too confused. And we'll see where the correct answer. So really it's this way. So probably what I would do, instead of checking in this, in case I made a mistake going from here to here, I would check in my original inequality. So going back and checking 0, is 0 over 5 greater than 4? And that's false, so I shade this direction. Let me do another one. Try not to mess it up this time. In this one, number 7, I have -1/3 b. Multiply by the reciprocal, which is -3 over 1, to get 1b. Multiplying by -3 over 1, and I'm multiplying by negative, so flip goes the symbol. So b is greater than, and -6 times -3 is +18. So if this is 0 on my number line, 3, 6, 9, 12, 15, 18 might be right here. Circle my critical point. Now I'm going to check 0 in my original inequality. So -1/3 times 0, is that less than -6? Is 0 less than -6? That's false, so I'm shading this direction. So actually, when we do this multiplication and division, it's almost easy to check our test points in our original problems, and then it tells us which direction the sign goes. All right, I'll see you in class tomorrow, and remember, we'll be singing our song.